Welcome back, everyone, from the weekend. So today what we'll talk about is we'll derive the combined first and second law. And this is basically going to be our launch pad for all thermodynamic derivations. So what I handed out is this sheet right here. This is a table from the Sandler textbook. And it is, in the corner you can see it says important table, and I would tend to agree. This basically has everything that you need to know about the foundational principles of thermodynamics in one nice, convenient table. It has thermodynamic identities, which we'll be talking about, Maxwell Relations, what we'll be talking about, and different forms of the first and second law, including definitions of Helmholtz-Gibbs and relations associated with that. It has material property definitions, heat capacity, C sub V, C sub V, isothermal compressibility, coefficient of thermal expansion, Joule-Thomson coefficient. So when it comes to single component systems, this is all of thermodynamics contained in one table. So what we'll be learning is basically how we're going to derive all of these. We're going to derive most of them today. Some of them are definitions, but the principles of how we derive these we will talk about today. Some of them we'll miss. And then the only other modification that we're really going to have that's significant to this is when we start to deal with multi-component systems. So the starting point for this here is the combined first and second law. So what we're going to do is start off with, again, an arbitrary system. We're going to hold temperature and pressure constant. We're going to have mass flowing into the system, and then potentially heat and shaft work flowing into the system. Now you'll note that the volume is not constant, which means that you can have the whole system expanding and contracting. We'll start off with the differential mass balance. So the rate of change of mass in the system is simply going to be equal to the mass flow rate going into the system. Pretty straightforward. There's no exit stream here. In terms of our energy balance, we have the total rate of change of energy in the system. And I'm just going to substitute in the mass balance into the energy balance so you don't have to use the m dot notation. This is the energy flowing into the system in the form of enthalpy from the mass plus heat, work for pushing the surrounding system back, that's the PV expansion work, and shaft work, sort of an impeller, turbine, some other process extracting work. The entropy balance, the total rate of change of entropy in the system, entropy entering the system from the form of mass, plus entropy generation. So what we'll do to simplify this is instead of keeping all of these dt's hanging around, we'll just say that we're going to do this derivation over some dt. So that we can just kind of forget about it and make our notation a little bit more streamlined. So effectively all we're going to do is there's a common variable here that is shared between both. We're going to substitute the entropy balance into the energy balance equation, and that's going to be our combined first and second law. Right, so this equation here is always going to hold true. It's the second law of thermodynamics. This equation here is the first law of thermodynamics. It's always going to be held true. This has never been violated. This has never been violated. So if I take two nice equations and I put them together, it'll produce another equation that's also never been violated. And that will be our combined first and second law. So let's rearrange our equation here. Let's see, so we have T ds minus S dn of T minus S dot j equal to Q. Substituted into our first law. I'm kind of lumping terms together here, so all the dm terms I'm putting together, just so we can be clear. And then we have Q. So then we also have.
Should we have minus TS, Jen?
Yeah. Yes, sorry.
Okay.
Correct. So I just tried to organize it based on the differential terms that we have here. I think I copied all. So we have 1, 2, 3 terms, 1, 2, 3, 5, 6. Yes, got all 6 of them. Now, we'll be using this expression here in our idealized world where we're going to be predicting material properties. So in our idealized world, we're going to perform all of our magical calculations reversibly. And we're not going to have the added complication of adding or subtracting work. This expression here, what do we think this is equal to from one of our definitions? This is the Gibbs. So this is equal to how much Gibbs free energy is entering the system. So our combined first and second law, which is going to be the starting point for the rest of the discussion in this class, which is going to be the consequential results for all of our calculations, is going to be, oh, sorry, I made a mistake. That is a positive right there. This is the combined first and second law of thermodynamics. Why this is so consequential and why it's such a good starting point is because, as we stated, there are 3 primary variables of the universe when it comes to thermodynamics. A 4th, if we consider how big the system size is. Most all of our calculations, we're not going to care about the system size because we just want to know what the property measurements of a fluid are, or what's the composition of a certain phase. We have internal energy, entropy, real space, and mass. Now, if we divide all of these through by mass, then we can get this combined first and second law with respect to intensive properties as opposed to extensive. In this case here, these are the intensive forms. Everything has an underbar. This is in terms of molar quantities. A little hat corresponds to everything in mass quantities, or in here, not a function of mass. Sorry, the variables here are actual energy, actual entropy, and actual volume. So here's the problem, though. This is our combined first and second law. Now, of these variables, there are only two that we can actually measure in any sort of convenience. That is the mass and the volume. So if I want to know how my internal energy and entropy are changing, I don't have a means to do so because I have a variable of unknown on either side. So all of the complexity that you guys may recall from an undergraduate thermodynamics class is how do we transform energy and entropy into variables that we can measure more conveniently. And that's where it comes to all of the calculus, all the Maxwell relations, all the thermodynamic identities. Is the objective here is that the first and second law are defined in terms of properties that we cannot measure on their own. Instead, we'll convert it into variables that we can measure trivially. And this is why an equation of state, which relates between temperature, pressure, and volume or density of a fluid, is going to be the gateway into calculating all thermodynamic properties for materials. So it is way more complicated than just what is the pressure in this tank, what is the density in this tank, right? With an equation of state, we can calculate phase behavior, we can calculate energetic properties, we can calculate entropy, we can calculate everything for a fluid with an equation of state. So let us go over the math properties. So the first one is the chain rule of differentiation. Or the total derivative. So, because in thermodynamics there are only 3 variables required to fully describe everything. So if you know 2, you can calculate the third. What this allows us to do is we can take the total derivative, and I'll do this for the intensive form here. I want to know what is the total amount of change of the internal energy of a system. Now what I can do is I can keep track of this from ups and downs from different sources. So in the case of thermodynamics, because there's only 3 variables, I only have to keep track of the change of internal energy with respect to 2 other variables. So what that means then is that I can write out that the total change in internal energy is equal to the partial change with respect to, let's say, temperature. Oops. Yes. No, that's this. Oh, sorry, keep on screwing this up. Monday is not my day. Okay, so what we're saying here is that, let's do an analogy. Let's say this is the total amount of money in your bank account, and you want to know how much the value is changing. So what you can do is you can keep track of, oh no, I'm totally screwed up right now. This is not my day, guys, I'm sorry. So hold, change this variable, hold the other one constant, change this variable, hold that one constant. That is there, that is there. Yes, okay. We're good, sorry. So go back to the analogy. So the total amount of change in the money in your bank account is, let's say, how much the money is changing with respect to how much more you make, plus how much you're losing with respect to how much you spend. So in the case of Thermo, this is the gateway for us to translate between these variables to these ones. Now the reason that we can write this out, and in a real mathematical system, every, let's say, property of U, the internal energy, or let's just say variable x, you could think of this how you expand it with respect to y, z, w, t, something, 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 something. So in the real mathematical sense, you would expand this function to as many variables as necessary to keep track of all the different ways that that property could change in a connected system. But since Thermo only has those 3 variables, when we expand any one thermodynamic variable, we only have to expand it with respect to 2 others, or a third if we're going to do it for an open system with respect to dm or dn. So for an open system, this is for a closed. For an open system, we're not keeping track of the intensive property of u, we're keeping track of the extensive property of u. Correct. Or number of moles, particles, whichever. So one quick comment on the notation here. Let's grab this variable here. du, dv, and constant. So what we're saying here, this mathematical scribble says how much is the internal energy changing with respect to changes in density while holding temperature constant. So the reason why we do this in thermodynamics is it makes our lives a lot easier by only calculating property changes with respect to movement in one other variable. This little notation down here, strictly speaking, is for convenience. This allows us to remember how we're more or less starting our derivation for the system. But as you know from multivariable calculus, if you're taking a partial derivative, you are holding all other variables constant. But by keeping this notation down here, it reminds us of what ensemble that we're working in, which are the properties and variables that we're changing. In this case, it's T, U, and V. Helmholtz energy is going to be the native properties here. All right, so with this information here, we can actually go about and write down some general calculus relationships that can be applied for all thermodynamic functions. So everything that we're going to be writing out here is possible because we're limiting ourselves to 3 variables that we're working with at any given time. Well, not this one here. This one's actually just more general. So the other assumption we're going to be making about thermal functions is that they're not going to have any sort of crazy discontinuities, which means that we can manipulate them in certain ways with the confidence that we're not going to be developing sort of infinity functions. So what we're saying here is that if we take the reciprocal of a differential, it's just equal to 1 over the value. Now, if this was infinite or if this was 0, we would run into problems. So this is well behaved. That also means that we can switch the order of differentiation . So in this case here, let's say our function is x. In this case, we take a derivative with respect to y first, then z. That'll give us the same outcome as taking the derivative with respect to z, then with y. And we can do this because there's not going to be any discontinuities of these functions. The triple product rule is a general mathematical function, again, that we can come up with because we're limiting ourselves to a certain finite number of variables. So I'll write it out and I'll explain my quick-hand notation for how I can remember it. Oops. Just keep screen this up. So the way that I write out the triple product rule, the variable that's held constant moves up here, that moves there, that moves there. Do that 3 times, and we can get the triple product rule. Straighten this out again. And the last one that we'll cover is one called the chain rule. In this case, you can see that the numerator and the denominator of 2 partials multiplied together will correspond to, they'll basically just cancel each other out. So this is what we can do now. What this allows us to do, so if we put the first and second law down, here's our combined first and second law. Now this is based on the first and second law of thermodynamics that we just created a system, substituted one into the other. Conversely, we are going to take the total derivative or apply the chain rule in a clever way to give ourselves some relationships. So what we'll do is we will expand the internal energy with respect to 2 variables. In this case, we'll expand it with respect to S and V. So what that allows us to do is, I write this as d u ds at constant v ds plus d u d v constant s. This is from the first and second law. This is just general mathematics that's sort of dumb. It doesn't know anything about the system that we're trying to investigate. All that it knows is that the internal energy is only a function of 2 other thermodynamic variables. So we obviously know that thermodynamics has been developed for hundreds and hundreds of years. So the reason why it just conveniently works out this way is because we've selected this expansion to be convenient. Now we can see a connection, right? That is equal, and this is equal. This is how we derive thermodynamic identities. So assuming I did not screw up, if we look on our handout here for thermodynamic identities, which is the sort of in the middle, we have that temperature is equal to V, and pressure is equal to minus change in internal energy with respect to density at constant entropy. Oops. Any questions? How does everyone feel about all this? Does it make sense? So the end objective, just as a recap, so I guess we don't have to put the V on this side, but basically the whole objective of all this, right, is we want to get out of the dependent units of internal energy and entropy because I don't have an internal energy gauge. I don't have an entropy gauge, but I can measure temperature, pressure, and specific volume. That's the whole objective of all of this, just as a recap. So what we can also do is we can give ourselves a few other relationships here. We can translate the combined first and second law of thermodynamics into some other forms that will be useful starting points for other derivatives to take place. So we can rearrange this expression. Okay, this is for a closed system, and this is for an open system. Additionally, I'll just do this for the closed system. I'm going to use the definition of enthalpy. Where enthalpy is defined as the internal energy minus PV, but in this case we have to take the derivative of the whole system. Oops, sorry. U minus PV minus VdP. Right, so this is just the product rule, if I get my names right. Two variables that are multiplied together. This is how we expand it. I'm going to substitute in my combined first and second law. Remember, this here is just a definition. I just made up what enthalpy means. That's all I did. I'm going to substitute this in here. So we have TdS minus PV minus, oh, let's see.
Should it be positive?
This would be GDS minus PDU. These should cancel out, so I have something wrong.
The definition.
Oh, yes, correct. Yes, that's right. Thank you. Minus PDV plus P. These cancel out. And we can take exactly the same approach if we use the definition of the Helmholtz and the definition of the Gibbs. We can come up with very similar expressions where we also have to use the product rule for this TS chunk here. And that gives us that the change in Helmholtz is, and I'll put this for, let's leave it for a closed system. So let's just summarize these a little bit. Actually, I'll put them down over here. D, U, T, D, S, S, H is equal to all right, so what we've done, these basically all of these right here, these are still all forms of the combined first and second laws of thermodynamics, meaning that on all circumstances these are held true. If these equations are true, that means that we are not violating the first or second law of thermodynamics, which is good. But the interesting thing here to note is that our standard combined first and second law tells us that U is fundamentally a function of entropy and volume of the system. So if we expand U, the internal energy, with respect to entropy and volume, we will generate thermodynamic identities. So we think of those as the root variables of that function. It is easiest for us to work in variable changings of entropy and volume if we care about how the internal energy changes. Now in the case of enthalpy, the sort of root or primary variables of entropy are going to be, are entropy and pressure. Meaning that if we expand enthalpy with respect to entropy and pressure, we will develop another set of thermodynamic identities. For Helmholtz, it is a function of temperature and volume. We're getting close to units that are very useful. And for the Gibbs, it is temperature and pressure are the primary variables of the Gibbs free energy. This is why the Gibbs is oftentimes what we see the most of working in thermodynamics. And enthalpy has that pressure term, which is nice. All right, let's see. Back on track. So I will leave it up to a homework assignment for you guys to replicate this process here and derive basically most all of the thermodynamic identities. The last thing that I'll talk about before we get a little bit more specific to thermodynamics, right now we're just kind of talking a little bit more about general math, is deriving the Maxwell's relations. So if you look on the handout, where I have mine, the Maxwell relations are the first block after the definitions. They are a series of relationships. I will derive one of them here, and then it'll be up to you to derive the other ones on homework. So how we develop the Maxwell relations is we take two identities and we take advantage of looking at the partial derivative order. So in this case here, we're going to start off with two identities that we derived already. These are two identities that we derived right here by looking at first and second law of thermodynamics plus just some general mathematical principles for calculus. So we're going to take each of these two derivatives and do a little cleverness, and that's about it. So what we're going to end up doing here is taking the first partial derivative and then redifferentiating it with the partial derivative from the second one. Right, so notice that this is change in internal energy with respect to entropy, change in internal energy with respect to entropy. Now we're going to differentiate it again, but in this case with respect to volume. So if we substitute in our identity, this right here is just equal to temperature. So this is equal to the change in temperature with respect to changes in density at constant entropy. Now we're going to do exactly the same thing, but we're going to switch. So in this case, we're going to take the partial derivative with respect to entropy at constant volume and substitute in this identity. Substitute in the definition. This is minus. Everyone follow me what I did here. Now we'll notice that sort of our starting function here is internal energy. And the only thing that we've done different is we've taken the partial derivative with respect to specific volume and with entropy. But the only thing that's changed is the order that we took that partial derivative. Now, since that doesn't matter, that means these two functions are equivalent. So one of the Maxwell relations that we've just derived here is that the change in temperature with respect to volume at constant entropy is equal to minus the change in pressure with respect to entropy at constant volume. And this is one of the 4 Maxwell relations. There are 3 more left to derive, basically using different functions here. All right. So the Maxwell relations, I would not say they're particularly intuitive to look at it and understand what we're going to do with it. But what the Maxwell relations will allow us to do is to assist in our objective, I keep on erasing it, translating from U and S into T, P, and V. But it also highlights one other thing that I really want to emphasize with thermodynamics. In thermodynamics, everything is a function of everything. Temperature is a function of pressure. Pressure is a function of density. Density is a function of entropy. Entropy is a function of internal energy. Everything is a function of everything. So if you change one property, you are changing the properties of all the other materials in the system. That's why when we write out our partial derivatives, in order to keep ourselves sane and make it so that we can actually accomplish these calculations in any sort of reasonable fashion, that we force ourselves to follow paths of, let's say, constant entropy, or we follow a path of constant density or specific volume. Right? Because if I just haphazardly change temperature, I don't know if I'm modifying the density or the pressure of the fluid. Right? I can do both of those. So in Thermo, that's why we like to keep this little notation here to keep us sort of focused on what we're actually trying to accomplish. All right, 10 minutes. I think we can actually come to a good conclusion of why this is all so much math. So we're going to be relying on some of the identities and Maxwell relations that we have on our important equation sheet. So here's what our objective is going to do. This is our objective. We want our thermodynamic variables, enthalpy, entropy, internal energy, Gibbs, Helmholtz, in units of temperature, volume, and pressure. That is our objective. Rather, it's more like this. Those are what we're working with as closed systems. That is our goal. Because if we can accomplish this task, then we can apply all the laws of thermodynamics to properties that we can measure, and we can start to tabulate and collect data on how properties change. So for this particular example, we're going to start off easy. We are going to expand entropy with respect to temperature and specific volume. Now, if we can accomplish this task, that means we have done one of our thermodynamic variables. We've converted it from abstract units to ones that we can actually physically measure. We will take the total derivative, or use the chain rule. So we'll break this up into two parts. First, let's look at this partial derivative, and then we will look at the second partial derivative. So for partial derivative number one, this is something that I don't know what it means at all. What is the change in entropy with respect to temperature at constant volume? That's not something that it makes intuitive sense to me. So what we're going to do is we'll use the chain rule. And again, we're going to be clever with it all. We're going to basically expand this partial derivative to include changes in internal energy as well. So you'll notice that one of our rules that I have since erased, you can imagine that you could cancel out these du's on top and bottom, and we would come back with the same function. However, this partial derivative, as it turns out, is the definition of temperature. Or you can also think of this as being a thermodynamic identity. This one, we're actually just going to make up a variable for it. We're going to call it heat capacity. As it turns out, we don't really have a good way to handle this at all. So instead, what we're going to do is we're going to make a little note, a little reminder for us and say, you know what? I don't know how to handle this, but I think we might be able to measure it. So instead, we define this as heat capacity, and we just put it on our to-do list of a property to measure for the fluid. So in the case here, this partial derivative that we are manipulating is simply equal to the heat capacity over temperature. Our second partial derivative that we don't know what to do with, as it turns out, this one's a lot easier. This is just a Maxwell relation. This is equal to, actually you guys tell me, and the Maxwell relations, what is this equal to? Let's grab our useful relationship sheet. dP dt at constant what? V. So put it all together. We have developed a relationship for the change in entropy with changes in temperature and specific volume. It is equal to the heat capacity over the temperature with changes in temperature and this function here with respect to changes in volume. For the ideal gas, I have an equation of state, the ideal gas law. I have a partial derivative. How is the pressure changing with respect to temperature at constant volume? What is the answer for the ideal gas law? Evaluate this partial derivative. Or V. Yes? So, if I have a fluid that is an ideal gas, which, as it turns out, is a very inaccurate equation of state for most things that we care about. So I've got some magical volume element of fluid that is at some temperature 1, specific volume 1, and I want to know what is the change in entropy going to some temperature 2 and specific volume 2. What I will be doing is I will be integrating this expression here from T1 to T2, and I will be integrating this expression here from V1 to V2. So if I substitute in R over V, what is the integral equal to? Hopefully that looks somewhat familiar from ideal gas entropy changes. So it rings a bell at least a little bit for some folks. So entropy is the easy one to start off with. So we can also, I just want to, well, I'm sorry, I'm going to steal just a few more moments of our in-between class time. Hopefully it's not too far of a walk, but I want to get to the final conclusion here. We could repeat exactly the same process. ds, what is a function of temperature and pressure, so how much is the entropy change with respect to those two variables? We can come up with a similar expression. Instead, we have to rely on the definition of a different form of heat capacity. Right? In this case here, C sub P is defined as how much the the enthalpy changes with respect to temperature at constant pressure. So again, we have to make up another term that we have to measure. So we can do that. However, let us quickly go and calculate variables du. Right? So we want to get change in internal energy into functions that we can measure with an equation of state. Our combined first and second law of thermodynamics is going to serve as our starting point. So far, hey, we're A-OK with respect to volume. We're done with that one. So we just have to worry about entropy. Well, we're going to steal the derivation we just did over here. We have entropy, where did I put it here, as a function of temperature and specific volume already. So I'm just going to steal that expression, throw it in here. Again, it is dp dt plus dp dt constant. That's the ds minus p. I'm missing something. dv, I need that here. dv, okay. So if I just rearrange this all very nicely, temperatures cancel out here. I can combine these. So the change in internal energy plus am I missing a term?
The T. Temperature.
The temperatures cancel out. Oh, yes, so the T needs to be here, correct? Yes. All right. almost there. So in this case, I have, no, I have right here. So we're going to steal our derivation for entropy with respect to temperature and pressure changes. We're going to substitute it into our combined first and second law for enthalpy. And I will skip over the math in the interest of time. You don't have to fret too much about getting these correct because they are on your useful equation sheet. All right, one last exercise. Let's just do it for the internal energy here. We have an ideal gas where we have PV equals RT. So, everyone, very quickly, let's calculate this expression. So we have temperature. What is the change in pressure with respect to temperature for the ideal gas law? It is, let's see, P R over V. R over V minus P. So if we rearrange pressure, we get pressure is equal to RT over V. So we have T R over V minus RT over V, which is equal to what? 0. So what did that teach us about ideal gases? Correct. The density of an ideal gas has no significance on what its internal energy is. Does that make sense? For an ideal gas. What about for a real fluid? Does pressurizing a real fluid change its internal energy? Most certainly it does. So a lot of the expressions that we're used to when it comes to doing thermodynamic calculations are based on ideal gas ones. And you can do exactly the same calculation here for the pressure of an ideal gas. What do we think this expression should reduce to for ideal gas? 0. The enthalpy of an ideal gas is not a function of its pressure, because how the ideal gas is derived is basically by assuming that the molecules are infinitely far apart and don't interact with one another. So of course the pressure or the density doesn't matter. But for a real fluid, this is not 0. This is not 0. Further, for an ideal gas, C sub P is equal to C sub B plus R. Right? This is for an ideal gas only. So what we can do is we can take these expressions, compute this value here, and we'll find out that this only reduces to this type of a form if you have an ideal gas. But instead, you have a much more complicated function over here for any sort of a real fluid. We have accomplished our goal. We went all the way from the first law and the second law, using just general calculus, general multivariable calculus, and we have now converted everything that we care about into units of volume, temperature, and pressure. What that allows us to do then is if we can develop an equation of state that relates between temperature, pressure, and volume, we can calculate every thermodynamic property we care about. And that's the objective of all of what we're trying to accomplish in thermodynamics. So now we're going to see how we apply these things for real fluids versus ideal gases, and that's going to be the next objective. All right, still a few more extra minutes, but I wanted to get through that task there. Have a good week and see you all on Wednesday.